How you doing, guys? Welcome to Rutgers EC Capstone 2020. My name is Salvais, and I'm part of group number 60. Our project is about building a smart goggle. It's basically a system for visually impaired people. It helps them navigate around home environment. Um, so the way this entire system works is that there are three different parts. The first one is the device itself. The second one is a mobile application. The third one is an AWS server that we're using. Um, so the way these all come together and work is that first you have the device itself that has the network, the pre-built and pre-trained network that we have. It identifies basic objects. There are 80 basic sets of objects because the network is trained on Coco dataset, which is available online. You can check it out. There are 80 classes that it's trained on. That's the default version of the network that we have implemented. The second one is the mobile device. The reason why we have mobile device, the mobile app that is onto a mobile device, is because we would like to also implement a functionality of adding more objects to the pre-trained network. So when a user wants to add more objects to the pre-trained network, they take a 360 degrees pictures of the object. There are a minimum of 7 pictures that we advise for the taking, and then that user basically uploads those pictures to AWS. Now, AWS take these pictures and it runs a data augmentation script. The data augmentation script is basically a script that replaces background from all those pictures. It creates more data sets for the network to train on. So now we take these 80 pre-existing classes and then we add these more classes that we have that user has added, and then we fine-tune this entire network. So the reason why we fine-tune the network is because fine-tuning the network is very fast. So we're not retraining the entire network. So now AWS doesn't cost as much money because they cost us depending on how much we use it. So that's why we fine-tune the network. And now, so now we replace the previous network with this new network with more classes and better functionality. So the next time when a user turns on their device, the Jetson, it basically checks for the updates. And well, if you have just pushed a bunch of pictures, then the network has this new weights, and it would tell the Jetson that there's a pending update, and the Jetson would have to update before it can receive the functionality. So it would update and it would get the new weights. And this happens very fast because we're not really changing the structure of the network. We're only adding more classes. We're fine tuning and we're only changing the weights. So the file for the weights, the weight file is it's small and it's very easy to be replaced. So now we replace the older weights with the new weights, and now you have this new network that can identify more objects, and the depth has nothing to do with the objects. Basically, the depth is a secondary part that works with the network itself, which doesn't change by adding the objects. So now you have this entire new system that can do more than it did before. So that's the main implementation that we have as of now. There are some of the things that we wanted to do, but because of COVID-19 and the current situation, we weren't able to do it. We weren't able to collaborate. So we wanted to implement SLAM as well as a navigation system, more like something connected to Google Maps, something to make it to a bigger scale, not just a home environment, but to even outside. If a person wants to go from one place to another, they can actually walk there. And so we wanted to add all these functionalities, but we weren't able to because of the time as well as the situation. So that's the main gist of the project. I worked on the YOLO algorithm that we've implemented. YOLO algorithm is it's freely available algorithm for anybody to use. It's basically a state-of-the-art object detection algorithm. So we're using that algorithm, and we're basically taking some of the functionality of the algorithm. We're tweaking some of the things because we also want the depth information. So we're running that algorithm and we're getting the object detection, but then we're fine tuning that algorithm. We're adding more functionality. We're adding the object, the distance measurement for that. So that's what we're doing. We kind of took the structure and the weights, and then we tweaked that algorithm to do the things that we wanted to do. So that's the part that I worked on, the depth measurement and the tweaking of the YOLO algorithm. One of my colleagues named Zane, who will be talking next, he worked on the similar part. So I'm going to pass it to him. He's going to explain the depth measurement part as well as give a demo of what we've built. Thank you.
Hi everyone, my name is Zain Sayed and I'm part of Group 60 for Capstone 2020. On this project I worked a little bit on YOLO, but more primarily on distance approximation, which would work together with object detection. At first, in order to get this information about depth, we thought about using two different cameras and setting them up in stereo configuration, but quickly realized that in order to maintain our goals and keep within our scope, we would have to choose something else. So instead, we opted for an Intel RealSense camera, which would help us solve all of our problems. With its inbuilt accelerometer, gyroscope, and already implemented depth of field, we wouldn't have to worry about these things. So with these three instruments, we will be able to use a generated color gradient map in which each of these pixels are assigned a color, and that color would tell us how far away that point in the image is away from the camera. So I'd like to show you how we use that to improve on our YOLO algorithm. So as you can see in this image, the map provided to us by the camera very clearly defines what surfaces that are closer to us and those that are a little bit further away. We can tell by the scale on the right that objects that are closer will be marked with the deep blue, while those that are far away will have a darker red. To get a more robust understanding of how this works in the background, let's take a quicker look at how the scale adjusts when different ranges are perceived in real time. This is a sample environment where you can see how light and range affect the depth field of the RealSense camera. Notice how the slider on the right adjusts itself when it's moving. We use parts of these scenes to approximate distance using pixel information. Now that we have all these parts together, the results look a little bit like this. In addition to the objects being recognized, we also have a distance associated with them. As you can see here, my laptop and its mouse have a distance right after its probability of what it is. To get this distance, we take the coordinates of the bounded box, as you can see here in this image, and this next piece of code takes these coordinates and gets an average pixel depth of all the pixels inside the box and uses that to estimate how far away the object is away from the camera. Now that you know a little bit about object detection and distance approximation in our project, I'd like to pass it on to my teammate.
So this is the app done by Max Davitalis. We're gonna add user credentials. Now we're gonna press add new object. We're gonna put the name of the object. So in this case, it's USB drive. Then press add pictures. So we're gonna take 2 pictures of this. Normally you want to take more. It's limit of at least of seven pictures. You should have at least minimum of 7. This is the demonstration of a data augmentation program that is created by Max Davitalis. As you can see, that's the program that we will be running. This is normally done on AWS. These are the keys, the objects that we will be running it on, and that's the code that we will be running. So as you can see, there are more pictures created with different backgrounds. There's a little bit of overlap, but that could be smoothened out. And this is where we store the backgrounds. As you can see, if you store more backgrounds, there will be more pictures that would be created. There you go. Yep. So that's how it works.
Hello, my name is Andrew Koskinen, and I'm working on the project Smart Goggles as part of Group 60 for the capstone project that we've been working on. So I've been extensively working on two separate projects here, basically, within the project, which is the AWS pipeline here, utilizing Amazon services and buckets, and as well as I've been working on the hardware components, ordering hardware and creating the CAD design, which is the computer aided design of the project, which is the smart goggles, of course. So I've been working on both of these things extensively. This AWS pipeline essentially allows us to store the images from our smart goggles and upload those photos in real time with the pipeline to the buckets. And the buckets then allow you to process the photos and change the backgrounds on the photos. And I'll go into that right now, actually. So here we have the image store, and we go into this bucket and into public, and we see that there's two different files here. We can go with the top one. There's a bunch of different files here with different objects. We'll use charger. And so in here you can see that this is a photo of an Apple charger or the wall brick. And we're going to back out here, and there's another photo of the wall charger, and this is just a different orientation. The reason we do this is so that we can get multiple angles and photos of slams, for slams, so it's realistic, because the camera, this is essentially a test. We utilize the camera to actually take these photos, but we take them individually, not using the app application because these are test files. But using the Intel RealSense Depth Camera D435i here, we are able to take these still photos and upload directly to the AWS pipeline here. And this basically enables us to image process it using a different bucket that pulls our scripts. So we have a link to our GitHub account, and there's actually a Python script that goes through this bucket, and we'll be able to find, it will pull the new files that have just been taken via the camera, and it'll take these new files, for instance, the charger files, and it will upload them using the GitHub script, Python script that we've written, and it will actually change the backgrounds of them to different colors. And the reason we do this is so that it can actually increase our object detection accuracy, as well as be able to distinguish what is background versus what is the object we're trying to detect here. So we'll take those photos, and we'll use multiple of them and change the colors, and then we can send that to a different bucket where we store it, and then be able to pull it from the application, which will in turn be able to find out what object that is, which we'll go into in more detail with my partners. Further along the line, basically this houses all of the images and the storing of them, as well as the image processing that goes on, and the convenience of adding GitHub to just access the Python scripts. And if you can see this little refresh button here, this basically doesn't need to be clicked unless you're just testing something yourself here. But if you take a photo using the application, it actually updates it in real time because it's adding a new piece of data here, and therefore it realizes that and will send it over via image processing. Okay, and now I'm going to actually go into the CAD design. So if you check over here, we have the computer design that I've created here. So these are the glasses. This is probably like the third prototype we've been working on for it. But the concept is that there is a electronics box here. This houses the TX2. As I mentioned, there's different ports on the sides here. These have all been cut out so that I can fit the different ports on the side here without actually opening the box. This is ease of use, so you can also fit different components and connect them to the chip here. And then this front part here is actually the housing for the camera, which obviously only needs the two camera pieces here because the IMDs don't really need to be visible for this to work. So they only really need these two cut out. And the top here actually just plugs in around the side here. They'll be able to plug directly into the electronic component here. This is the only part of the actual camera piece inside the mount on the bottom that needs to be accessed. We don't really need to access the mount though, because this will stay in there. It's basically perfectly fitting it. It's got actually both of these housing objects fit the components that they're required to fit by about 5 millimeters of wiggle room there. So they should fit pretty snugly. As well as these tops are obviously removable, as well as you can we were going to add either a latch for when we created the real one, or just hot glue, for instance, like the bottom. And further than that, also, these headphones are not just for show, as you might have thought, because they're just made of plastic. But if you look in here, see that it's actually hollow, and you can fit Apple headphones or any headphones that you would like inside here, and actually wire them around to both ears, and then plug in directly to this port on the Jetson, which would allow you to receive audio for the instructions for the project, so for smart goggles. And further than that, the current specifications that we have, as well. Oh, one more thing, the actual headpiece here, I almost forgot. The way that I measured this headpiece, because I don't really have access to my colleagues at Rutgers at the moment, is I actually utilized my family of 5, which allows me to get a pretty accurate head size for what I think would be able for people to fit in this. So if that's a little off, then blame my family's unusual head size. But other than that, that's the best way I could conceive of creating a replication of this. So they didn't really mind because, coronavirus, not really anyone doing that much. So I used a tape measure to measure their head for the head size. But further than that, that is about it on my side for the project. So now I'll hand it off to my partners. Thank you.